Hey Science 10, welcome to lesson 2 of your physics unit. I'm going to do a few smaller videos this time rather than doing one long one like I did last time, just to keep it simple. Okay, so in the first video we're going to talk about constant motion and uniform motion, and we're going to talk about constant speed and calculating speed, okay, in the first video. Okay, so moving on to there's a few terms that you must really know, so these two are very important terms. Scalars and vectors. So what a scalar is a quantity which is fully described by magnitude alone. So it just describes magnitude. So it might be how much or how many. For examples of this would be speed and distance, and there's a few more examples on the next slide too. So if you are driving 20 kilometers an hour, that is a speed, it is a vector. If you are going to run 20 kilometers, good for you, is also a scalar. Okay, a vector is something that has magnitude but also adds direction. Okay, so it adds direction to it. So if you were going to run 20 kilometers southwest, still good for you. It now is a vector quantity because it has direction. If you're going to drive 20 kilometers an hour north towards Edmonton, that is now a vector because you've added direction. The reason why there's a difference is one calculates velocity and one calculates speed, and it's easy to recognize, and that's not speed. Okay, those aren't the only two differences, but the V's kind of line up for these two, so I kind of use them. Okay, so it's important to know it because sometimes direction is important to physics equations, sometimes it isn't. Okay, so moving on here, let's talk about this a little bit. A scalar right here, this is a scalar because this car is driving 20 meters per second because speed should always be written in meters per second. But this arrow showing which direction it is, you don't know, okay, it's not there. So it's 20 meters per second, it is a scalar, okay. This is a vector because you can see this arrow very clearly, it's not x'd out. This is going 20 meters per second at a 30-degree angle up a hill, okay. So it is going up a hill at 30 degrees, it is a vector, okay. Other examples of scalars versus vectors might be distance, speed, time, mass, those kind of things. Whereas vectors are displacement, velocity, acceleration, and those kind of things. And a big thing we're going to be talking about in this little video and the next one is speed versus velocity, okay, like I just mentioned in the previous slide. Okay. Three more terms that are very important for this unit are going to be the difference between speed, distance, and displacement. Position, distance, and displacement. So a position is your location in space described in terms of a distance and direction from the reference position. So let's say, for example, Edmonton is 400 kilometers north of Brooks. Okay, I don't know how accurate that is. I just made that up. But that would be a vector. That would be a position. It has direction and distance, so we're good. Okay, distance alone is a scalar, and that's the length of a path. So I like this picture down bottom quite a bit. Okay, so that red line that shows the distance here. So if you start here, let's say you run all the way to the golf course, this is the path you've taken. Okay, and let's say you've ran 2.5 kilometers. Okay, that's supposed to be a 5. Okay, the distance you've traveled is 2.5 kilometers. Whereas this from here to here is your displacement. So your displacement is simply the difference between point A and point B. Okay, so you go through all the hills, go through all the buildings, go through all the trees or whatever that obstacles are in your way. You just pretend they're not there and it's a straight line between the 2 points. So the displacement will always be smaller than the distance unless of course the distance is perfectly straight line as well, and then they will be equal. Okay, so this, as a displacement, you couldn't just write, let's say this is 1.2. You couldn't simply say that you ran, that the displacement is 1.2. Let's say it's 1.2 kilometers southeast. Okay? So that's the difference between displacement and distance, okay? And we use those terms very differently. They call displacement, they write it like this, okay? So this means change, okay? This here, this triangle means delta, and what delta means, anytime you see delta, it means change in, okay? So this is distance, this is final, this is initial, displacement final, displacement initial, so you take away the distance the final distance, or the initial distance from the final distance, and you find the change in the two. Okay, so that's how you calculate it. And also with vectors, you will often see those arrows above the letters. That will also give you a hint to say that it is a vector and not a scalar. Okay. Another example I like to use is a golf course example. I'll just go further with it. So basically, let's say you are going for a run with the cross-country team, and the golf course is exactly 2.5 kilometers away. We'll say golf course here, school here. So you run out there with your cross-country team. You've ran 2.5 kilometers. You run back. The total distance you've run is 5 kilometers. But you go all the way there. You end up at the exact same spot that you finished. So your displacement is actually 0. Okay, so you have a displacement of 0 because the final and the initial place is the exact same. Okay, so that's another way of looking at it. So moving on, another example, exact same thing. Richard walks 1.5 kilometers north to the Dutchess station from his house. So he walks 1.5. On his way home, he stops 0.75 kilometers towards his house at Jessica's. Okay, these are kind of like equations on a number line or integers on a number line, so they got to have opposite signs when you're talking about vectors. So Richard walked a positive 1.5 kilometers, okay, 1.5 kilometers north, and he walked a negative 7.5 kilometers south. Okay, so in order to find his displacement, it's 1.5 subtract 0.75. Okay, and he will get 0.75 as his displacement. Okay, so he is actually 0.75 kilometers north. Okay, his total distance that he walked would be 2.25. You can simply add these two numbers together because that he did walk that whole distance. But remember, in displacement, if they're going in opposite directions, you've got to subtract one from the other. Okay, so remember that. Uniform motion, we're going to get into uniform motion. So uniform motion is in a straight line at the same speed the entire time. So you are driving 20 kilometers an hour in a straight line constantly, okay? It very rarely happens, but that's what uniform motion describes. So speed in this equation is the distance an object will travel in a certain unit of time. Now you might get meters per second, you might get meters per hour, you might get kilometers per hour, you might get kilometers per minute, those kind of things. But that's essentially what it is. Now, average speed, this is the equation for average speed, okay? So it's V av equals delta D over delta T. So change in distance and change in time. So basically, if you're driving 20 kilometers an hour, you take your distance divided by your time to get your speed. So let's say you've traveled 100 kilometers in 5 hours. So 100 in 5 hours. So you just divide them, and then you get your average speed in those units. Okay, I should always write kilometers an hour. Okay, I would prefer, and it might be a good idea for you guys, instead of using this equation, you write speed equals change in D over change in T. While it might not be confusing right now, when you get to velocity, velocity is also the exact same equation as this. Okay, and then it could be confusing when you're trying to do the same question. Some of you will be able to get it straight, some of you will struggle with that, so that would be my suggestion. Okay, so here's the practice question for you. I'm going to do the next practice question instead, or the next slide, after this little tidbit. So constant speed states that something is traveling at the exact same speed for a length of time. This rarely happens, so we all know when we're driving, we get behind somebody slow, or we accidentally press on the gas too much, or we see a red light or a stop sign, things like that. It rarely happens in life. Average speed and constant speed are not the exact same time, but for our lesson, okay, we pretty much use them interchangeably, okay? So basically, if you are driving to Medicine Hat and it's 100 kilometers away, which I know it isn't exactly, and it takes you an hour to get there, you can assume you're going 100 kilometers an hour, but that's not exactly accurate because you know that we stopped at a few of those stoplights in Redcliffe and entering Medicine Hat, and it took 2 or 3 minutes. We slowed down leading up to them. We accelerated out of there, but we just take total time and total distance, and that gives us our, for this unit, constant speed, but really what it is average speed, okay? Yeah, so let's talk about this example here. So Freddy Krueger is chasing you. Obviously, you're sleeping. If you run, it should say run, to the nearest hiding spot, 17.9 meters away, it takes you 3.2 seconds to get there. What's your average speed? Okay, so average speed, I'm going to use S equals change in T time over change in, sorry, this should be change in distance over change in time. Okay, which is S equals, I wish I could write smaller with this. So my change in distance is 0. So I start at 0, okay, and I'm 17.9 meters away. So 17.9 subtract initial is 17.9 meters, okay. And I started at 0 again, so it's 3.2 seconds, minus 0 seconds, so it's 3.2, so it's very easy when you start at 0, okay? And I do that division, okay, and I get, I believe, 5.6, I've already done it, 5.6 meters per second, okay? Okay, and I could tell that it's, these are my units right here, meters per second. Okay, so this, at this point, you can do up to page 16 in your notes, I believe. Okay, so good luck to you. Feel free to ask me questions if you need to, and I will have a new unit or a new video moving forward. Thank you.